We begin our discussion of section 3.5, the fundamental theorem of arithmetic. What is the fundamental theorem of arithmetic? Here it is. Theorem 3. The fundamental theorem of arithmetic says the following. Suppose A is an integer number which is greater or equal to 2. Let us consider factorizations of A. P1 times and so on Pm and Q1 times and so on Qn, where P's and Q's are prime numbers. The fundamental theorem of arithmetic says the following. M is equal to N, and Q's can be reindexed, so then Qi is equal to Pi for all i's. In simple words, factorization of an integer greater or equal to 2 is unique up to the order of terms. Now, some people say that the fundamental theorem of arithmetic is kind of obvious because we cannot write an integer into fundamentally different ways as the product of prime numbers. However, this is actually a highly non-trivial fact. Here is why. Please take a look at the following example. Note that there are distinct integers n1, n2, n3, and 4 such that n1 times n2 is equal to n3 times n4. For example, 1 times 6 is equal to 2 times 3. n1 is 1, n2 is 6, n1 times n2 is equal to n3 times n4. However, there are no distinct prime numbers P1, P2, P3, P4 such that P1, P2 is equal to P3, P4. So, there are distinct integers such that this is true, but there are no distinct prime numbers such that this is true. To make this fact even more non-trivial, let us go back to elementary school. Let us think about what is multiplication. So, according to what is written here, there are distinct integers n1, n2, n3, and 4, such that n1 plus n1 plus and so on plus n1 and 2 times is equal to n3 plus n3 plus and so on plus n3 and 4 times. But there are no prime numbers such that P1 plus and so on plus P1, P2 times is equal to P3 plus and so on plus P3, P4 times. And now, looking at this, what is written here is a highly non-trivial result. Why this is possible? But if we impose an extra condition, namely, if these integers are distinct prime numbers, this is impossible. How to explain it? Why is that?
I don't know if we've proven this yet or if we could assume it, but it's because if you have a product of two integers, then that product has factors which are the factors of the two integers.
And why is that?
Mm,
Once again, note that this number is divisible by n3, it is divisible by n4, also it is divisible by n1 and n2. However, this number is divisible by p3, it is divisible by p4, but it is not divisible by p1, and it is not divisible by p2. Why is that?
Professor?
Yes.
We can prove it using Euclid's lemma.
What do you mean by Euclid's lemma?
So if prime p divides the product of AB, of two integers product AB, then prime p must at least divide one of those integers.
Wonderful. You are talking about Theorem One. Is this what you are talking about?
Yes.
So guys, indeed, in order to prove the fundamental theorem of arithmetic, we need a bunch of theorems. And theorem number one is the following. Suppose A, B, and C are positive integers such that A and B are relatively prime. Suppose also A divides BC, then A divides C. Note that if we skip this condition, what is written here is not true. And here is a control example. Please take a look at this. Note that 6 divides the product, but 6 does not divide 2, and 6 does not divide 3. So if we skip this condition, and indeed over here 6 is not a relatively prime with 2, 6 is not a relatively prime with 3. If we skip this condition, this conclusion is not necessarily true. Sometimes A divides BC, but A does not divide B, and A does not divide C. However, if A and B are relatively prime, and if A divides BC, then A divides C. Now let us prove it. Let us go back to Theorem 2 from section 3.3. By Theorem 2, the greatest common divisor of A and B can be written as their integer linear combination. Note that since A and B are relatively prime, the greatest common divisor is equal to 1. So, by Theorem 2, the greatest common divisor can be written as an integer linear combination of A and B, but the greatest common divisor is equal to 1. So, there are integers S and T such that SA plus TB is equal to 1. Here is what we do next. Let us multiply both sides here by C. If we multiply both sides here by C, we get this. Since A divides BC, A divides TBC. This term is also divisible by A. Since both terms are divisible by A, their sum is divisible by A. Now we use Theorem 2 from section 1.5. So the left-hand side is divisible by A, therefore the right-hand side is divisible by A. It's exactly what we wanted to prove. Repeat once again. Step 1. The greatest common divisor is equal to 1. By Theorem 2 from section 3.3, the greatest common divisor can be written as an integer linear combination of A and B. But the greatest common divisor is 1. So 1 can be written as an integer linear combination of A and B. Multiply both sides by C. Done. This term is divisible by A. Since BC is divisible by A, according to what is written here, TBC is divisible by A. So this is divisible by A, this is divisible by A. Therefore, by Theorem 2 from section 1.5, the whole left-hand side is divisible by A. Since the left-hand side is equal to the right-hand side is divisible by A. C is divisible by A. This is exactly what we need.
Sorry, Professor, just to clarify, A and B only have to be co-prime. They don't actually have to be prime, right?
Yes, exactly.
Yeah, okay.
Note that when we say numbers are relatively prime, this does not necessarily mean that A and B are prime. Here is an example. Note that 9 is not a prime number. 4 is not a prime number. But 4 and 9 are relatively prime numbers. When we say relatively prime, this means the following. A and B do not have a positive divisor greater than 1.
Okay, thanks so much.
Other questions?
Could you clarify how this proves that a product of two primes cannot equal the product of two distinct primes?
Very good question. Yes, we can use Theorem 1 in order to show that this is impossible. Here is how. Note that if there are distinct prime numbers, P1 and so on, P4, such that P1, P2 is equal to P3, P4, P3, P4 is divisible by P1. Since P3, P4 is divisible by P1, so we have this. Think about B as about P3 and C as about P4 and A as about P1. P1 divides P3, P4 according to what is written here. On the other hand, P1 and P3 are relatively prime because P1 and P3 are prime numbers. Moreover, these are distinct prime numbers. Since P1 divides P3, P4, and since P1, P3 are relatively prime, by Theorem 1, P1 divides P4. This is impossible because P1 and P4 are distinct prime numbers. We're done.
Nice. Thanks.
So Theorem 1 is actually a really powerful result. The proof is short, but note that when we prove it, we make two references on Theorem 2 from section 1.5 and on Theorem 2 from section 3.3. And let me also remind you that in order to prove Theorem 2 from section 3.3, we use the division algorithm. And the proof of the division algorithm, it's over here. The proof of the division algorithm is actually pretty long. So don't be fooled by this short proof. If we expand this and expand this, the proof of this result is actually pretty long. Next. So we discussed one application of Theorem One. This result. This is impossible. But now let us go back to irrationality of square root of 2. Let me remind you that we already proved that square root of 2 is irrational. Here is the proof. We used the well-ordering property, and the proof was not short at all. However, we can prove that square root of 2 is irrational much shorter. Please take a look at this. We just see this proof is significantly shorter than this proof. It's over here. It's 1 page long. Here we have just few sentences. Sentence number 1, number 2, number 3, 4, 5 sentences long. We are about to discuss this proof. However, before we discuss this proof, let me give you yet another proof of the fact that square root of 2 is irrational. I give proof 2, this will be proof 3. I give proof 2 in order to help you appreciate this relatively short proof even better. So guys, if you Google irrationality square root of 2 in most sources, the default proof is this proof. Let us go over. So, as before, we assume to the contrary that square root of 2 is rational. Rational means the following. Square root of 2 is a divided by b, where a and b are integers. Moreover, the denominator is not equal to 0. Now, in proof 2, sentence number 2 is the following. Without loss of generality, we can assume that a and b are positive integers. To the contrast, in proof 2, sentence number 2 is the following. Without loss of generality, we can assume that a and b have no common divisor greater than 1. And now the question is, how come that without loss of generality, we can assume that a and b are relatively prime? Well, guys, please take a look at the following. Suppose square root of 2 is equal to a over b, and suppose a and b have a common divisor. Let us denote it by k1, which is greater than 1. Common divisor means the following. A, which is over here, is equal to a1 times k1, and b is equal to b1 times k1, where, of course, a1 and b1 are integers. So, let us copy this over here, and then I'll replace a by this expression and b by this expression. We get this. Obviously, k1 a common divisor can be cancelled. We get A1 over B1. So if square root of 2 is equal to A over B, square root of 2 is also equal to A1 over B1. Now, if A1 and B1 also have a common divisor, let us denote it by K2. K2 also can be cancelled. And we get the following. Square root of 2 is equal to A over B, which is equal to A1 over B1, which is equal to A2 over B2, and so on. Let us cancel common divisors until at some point top and bottom do not have common divisors. Let us denote such a top and such a bottom by AI and BI. Conclusion. If square root of 2 can be written as integer over integer, square root of 2 can be written as integer over integer where top and bottom have no common divisor. Therefore, let us assume from the very beginning that top and bottom do not have common divisor. Once again, in short, if square root of 2 is equal to integer over integer, and these two integers have a common divisor, cancel it out. Here is what we do next. Let us square both sides here. Done. Let us multiply the left-hand side and the right-hand side by b squared. B squared is gone on the right. What is left is a squared. And the left-hand side becomes 2b squared. Observe that 2b squared is divisible by 2 because it is of the form 2 times integer. Since the left-hand side is divisible by 2 and the left-hand side is equal to the right-hand side, the right-hand side is divisible by 2. Now, we will prove in a moment a lemma that says the following. If a square is divisible by 2, then a is divisible by 2. Since a is divisible by 2, a can be written as 2 times k, where k is some integer. And now let us replace a over here by 2k. Done. 2k squared is 4 times k squared. We expand parentheses. And lastly, let us cancel out 2. Done. Now, let us apply same logic as before. The right-hand side is of the form 2 times integer. Therefore, the right-hand side is divisible by 2. But the right-hand side is equal to the left-hand side. Since the right-hand side is divisible by 2, the left-hand side is divisible by 2. But by the same lemma, b is divisible by 2, since b squared is divisible by 2. We get a contradiction. Why? According to what is written here, a is divisible by 2. According to what is written here, b is divisible by 2. But from the very beginning, we assumed that a and b have no common divisor greater than 1. So, we assumed to the contrary that square root of 2 is rational, we got a contradiction, therefore square root of 2 is irrational. Now, here is how we prove the lemma. So, we want to prove that for all integers n, if n squared is divisible by 2, then n is divisible by 2. We will prove it by contradiction. Assume to the contrary that there exists an integer number n such that n squared is divisible by 2, such that this is true, but n is not divisible by 2. Since n is not divisible by 2, by the division algorithm, n is equal to 2k plus 1. Here is why we need division algorithm here. Note that by the division algorithm, and actually let me go back to the division algorithm. Note that by the division algorithm, if b is equal to 2, if we divide a by 2, there are only two possibilities for the remainder. A remainder is either 0 or 1. Since here we say that n is not divisible by 2, a remainder cannot be 0. Conclusion, the remainder is 1. Basically, this is exactly what we are talking about here. Thanks to the division algorithm, for any integer n, there are only two possibilities. It is of the form 2q, it is either divisible by 2, or of the form 2q plus 1, it is not divisible by 2. Since here we say it is not divisible by 2, it is of the form 2k plus 1. And now, let us square this number. N squared is equal to 2k plus 1 squared. We expand parentheses. 2k squared is 4k squared. 1 squared is 1. And finally, the middle term, 2 times 2k times 1, which is 4k. Next, let us factor out 2 over here. Done. And lastly, let us replace this term, 2k squared plus 2k, by m. Since k is an integer number, m is an integer. Conclusion, n squared is of the form 2 times integer plus 1. Since the remainder is 1, n squared is not divisible by 2. We got a contradiction. Here it's written n squared is divisible by 2. Here it's written n squared is not divisible by 2. We got a contradiction which proves the whole lemma. All right, guys. So we discussed two totally different proofs of this theorem. One proof is a page long. The other proof is almost a page long. Now, please take a look at this proof. Only 5 sentences. However, in order to come up with this proof, we use Theorem One, which is a really powerful result. So, sentence number 1 and sentence number 2 here are same as sentence number 1 here and sentence number 2 here. So, as before, we assume to the contrary that square root of 2 is a rational number. Without loss of generality, we assume that A and B are relatively prime. Also, as before, we square both sides here, done. and multiply both sides here by b squared. Done. So once again, this portion is a copy of this. However, this sentence is different from this. Note that over here we observe that the left-hand side is divisible by 2. Since left-hand side is divisible by 2, or right-hand side is divisible by 2. However, note that the left-hand side is also divisible by b, because 2b squared can be written as b times integer. This is exactly what we use here. The left-hand side, which is written over here, is divisible by b. Since the left-hand side is equal to the right-hand side is also divisible by b. But now let us use Theorem One above. Observe that a squared is equal to a times a. So b divides a times a, and b and a are relatively prime. So once again, over here it's a little bit confusing. We have a different choice of a's, b's, and c's here and here. In Theorem One, we start with the following. Suppose a divides the product of two integers, and a is a relatively prime with one of these integers. Then a divides the other integer. It's exactly what we have here. b divides the product of two integers, a and a. b is relatively prime with a. Therefore, b divides a by Theorem One. In other words, if over here b and c are equal, as a corollary from Theorem One, we get the following. If a divides b squared, and a and b are relatively prime, a divides b. It's exactly what we have here. If b divides a squared and a and b are relatively prime, b divides a. Since b divides a divided by b is an integer. It gives us a contradiction. Square root of 2 is not an integer. Done. Folks, any questions here?
Don't we get a contradiction from so after applying Theorem One, b divides a. So wouldn't we not even need a divided by b, being an integer, but because we already know that b divides a, but we assume that the greatest common divisor between a and b is 1?
No, because we've never said that b is not equal to 1. b is not equal to 0. Indeed, if b divides a, the greatest common divisor is b. But where is the contradiction?
Okay, I think I see now. All right.
You see it now? So this is the fastest way to get a contradiction. Since b divides a over b is an integer. But we know that square root of 2 is greater than 1 and lesser than 2. So square root of 2 is not an integer. We got a contradiction. See it?
Yes.
Corollary. Suppose a, b, and c are positive integers such that both a and b divide c. Suppose also a and b are relatively prime. Then their product divides c. So here's how we prove it. A divides c. By definition of divisibility, c is a times an integer. B divides c. However, c is equal to am. So if you replace c by am, we get the following. B divides am. But note that according to what is written here, b and a are relatively prime. Since b divides the product and b and a are relatively prime, by Theorem One, b divides m. But now again, by definition of divisibility, b divides m means the following. M is equal to b times some integer. Now let us put pieces together. According to what is written here, c is equal to am. According to what is written here, m is equal to bn. Now over here, let us replace this m by bn. If we replace m by bn, we get the following. C is equal to a times bn. It's exactly what is written here. But this, by definition of divisibility, means c is divisible by ab. It's exactly what is written here. Let us discuss the following example. Prove that the product of any three consecutive integers is divisible by 6. Here we prove it in two different ways. One way to prove it is the following. By the division algorithm, there are only 6 possibilities. K is of the form 6q, or of the form 6q plus 1, or of the form 6q plus 2, and so on, or of the form 6q plus 5. And now let us first plug in 6q into this expression. Note that this is the product of 3 consecutive integers. Or replace k here, here, and here by 6q. Done. We see that if k is of the form 6q, the product of 3 consecutive integers is divisible by 6, because this can be rewritten as 6 times an integer number. Case number 2, suppose k is of the form 6q plus 1, or replace k here by 6q plus 1, done. Then factor out here 2 and factor out here 3. 2 times 3 is 6, divisible by 6 again, and so on. So, conclusion, no matter what is k, the product of 3 consecutive integers is divisible by 6. But now here's a problem with proof 1. It's long. Is it possible to prove that the product of any 3 consecutive integers is divisible by 6? Easier. Please take a look at proof 2. Suppose k is an integer number. Note that there is only one integer between any 2 consecutive even numbers. Therefore, either k or k plus 1 is even. Since either k OK plus 1 is even, the product of three consecutive integers is divisible by 2 no matter what is k. Similarly, since there are only 2 integers between any 2 consecutive numbers divisible by 3, either this or this or this is divisible by 3. For example, there are only 2 integers between 6 and 9. There are only 2 integers between 9 and 12, and so on. Therefore, no matter what is k, either k or k plus 1 or k plus 2 is divisible by 3. Therefore, the product of three consecutive integers is divisible by 3. And observe that 2 and 3 are relatively prime. So, this is divisible by 2, this is divisible by 3, 2 and 3 are relatively prime, therefore this is divisible by 2 times 3 by 6 by the corollary above. Now theorem 2. If P divides the product of n numbers a1, a2, and so on, an, and P is a prime number, then there is an integer I such that P divides AI. Repeat once again. Let P be a prime number. If P divides the product of n numbers, a1, a2, and so on, an, where these numbers are positive integers, then P divides at least one of these integers. Let us prove theorem 2 by induction. Step 1. For n is equal to 1, the case is trivial. Here's why. If n is equal to 1, here we have just a1. Obviously, if P divides a1, there is an integer I such that P divides ai. This integer is 1. If P divides a1, it divides a1. Step 2. Assume that the result is true for some n is equal to k, where k is greater or equal to 1. That is, if P divides the product, P must divide at least one of the factors. Now we prove it for n is equal to k plus 1. So, consider the product of k plus 1 integers. Let us denote this, the product of k integers, by c, and let us denote the last integer by d. Note that since p is a prime number, there are only 2 possibilities. Either the greatest common divisor of P and C is equal to 1, or the greatest common divisor of P and C is equal to P. Here's why. The greatest common divisor is a divisor of both numbers. But note that there are only 2 positive numbers that divide P. It's 1 and P. Therefore, the greatest common divisor of P and C is either 1 or P. Now, Case 1. Suppose the greatest common divisor of P and C is equal to 1. This. In this case, we use Theorem 1. So, P divides this product, P and this, P and C, are relatively prime. Therefore, by Theorem 1, P divides the last term, AK plus 1. And we're done. So, in case 1, there is I such that P divides AI. I is equal to K plus 1 because P divides AK plus 1. Case 2. Suppose the greatest common divisor of P and C is P. This means P divides C. This. But now let us use step 2. Since P divides the product of K integers, by step 2, there is at least one integer which is divisible by P. So no matter we have case 1 or case 2, P divides one of the factors here. Folks, any questions here?
Can you repeat the explanation of case 1?
Yes. Case 1. Suppose P and C are relatively prime. Now, remember what is C? C is this. So, over here, let us denote this product by C. P and C are relatively prime, and P divides the whole thing. Repeat once again. P divides C, AK plus 1. P and C are relatively prime. Therefore, by Theorem 1, P divides AK plus 1. Does this make sense?
Yes, absolutely. Thank you.
Folks, any other questions?
This is a question about GDCs in general. So essentially, whenever we're taking GDC, where we have some number, just denote this number by the letter C.
So once again, we start with two numbers, A and B, correct?
Yes, and I'm saying that, let's say A is equal to 0.
And suppose A is equal to 0. Okay.
Would the GDC be just B?
Yes.
Or it would just
Yes.
be B? Okay.
The answer is yes. So the greatest common divisor of two numbers, 0 and B, of course, B cannot be 0. The greatest common divisor of 0 and B is B, because B divides B and B divides 0. Was that your question?
Yes. All right. Thank you.
Next. Corollary. If P is a prime number and P divides A to nth power, P divides A. Here's how we prove it. Over here, put A1 is equal to A2 is equal to and so on, AN is equal to A. In this case, this product is A to nth power. So we read Theorem 2 in the following way. If P divides A to nth power, P divides AI. But remember, AI is equal to A. So if P divides A to nth power, P divides A. Done. Next. Now we are ready to prove Theorem 2, the fundamental theorem of arithmetic. Assume that an integer a, which is greater or equal to 2, has the following factorizations: p1 times and so on pm, q1 times and so on qm, where these p's and these q's are primes. Then, number 1, m is equal to n. It's exactly what is written here. And these q's may be re-indexed so that qi is equal to pi for all i's. In other words, factorization is unique. We will prove it by induction on L, where L is maximum of m and n. Step 1. If L is equal to 1, the given equation becomes A is equal to P1 is equal to Q1. And the result is obvious. Step 2. Suppose the theorem holds for some L is equal to K, where K is greater or equal to 1. We prove it for L is equal to K plus 1. So, A is equal to P1 times and so on Pm, which is equal to Q1 times and so on Qn, where maximum of m and n is k plus 1. Here is what we do next. By what is written here, since the left-hand side is divisible by Pm and the left-hand side is equal to the right-hand side, the right-hand side is divisible by Pm. It's exactly what is written here. Pm divides this. Now it's time to use Theorem 2. By Theorem 2, if a prime number divides the product, this prime number divides one of the factors. Let us denote this factor by Qi. But remember, Qi is a prime number. Prime number is a number which is divisible only by 1 and by itself. Since Qi is divisible only by 1 and by itself, and since it is divisible by a prime number Pm, and remember, Pm, a prime number, cannot be 1. Pm is equal to Qi. Repeat once again. Qi is divisible by a prime number Pm. Since Qi is prime, it is divisible only by 1 and by itself. Of course, here we are talking about positive divisors only. Therefore, there is no escape. Qi is equal to Pm because Pm is not equal to 1. Now, without loss of generality, we can assume that Qi is Qn. Why we can assume it? We can just re-index here. Or re-indexing here. Indeed, we may assume that Qn is equal to Pm. And now let us cancel out Pm and Qn. We get this. But now, since maximum of m minus 1 and n minus 1 is equal to k, we can use step 2. And by step 2, q's may be re-indexed so that Qi is equal to Pi for all i's. We are done. Folks, Think about questions here.
I don't think I understand exactly what the max function is.
Max means maximum. For example, if m is 2, n is 3, max of 2, 3 is 3. Maximum of these two numbers. Was that your question?
Yes, thank you.
Other questions?
I don't quite understand how by reindexing we assume that what was it, Qn equals Pm?
Very good question. So look, according to what is written here, Pm divides one of the factors here. Now, imagine that this Qi is actually Q1. Reshuffle, reindex these Qs in such a way that Q1 is on the last position. Done. Just switch the order.
Okay, I see. Thank you.
Next. Corollary. If an integer number a is greater or equal to 2, then there are unique, distinct prime numbers pi's and unique integers alpha i's, positive integers such that a is equal to p1 to the power alpha 1 times and so on, pn to the power alpha n. Here's an example. 120 is 2 cubed times 3 to first power times 5 to first power. Theorem 4. Theorem 4 says the following. Factor A completely, factor B completely. Then the greatest common divisor of A and B is P1 to the following power minimum of alpha 1 beta 1 times and so on Pn to the power minimum of alpha n beta n. For example, here's factorization of 720. Here's factorization of 2100. By this formula, the greatest common divisor of these two numbers is 2 to the following power minimum of 4 and 2, which is 2. 3 to the first power, because minimum of 2 and 1 is 1. 5 to the first power, because minimum of 1 and 2 is 1, times 7 to 0 power, because minimum of 1 and 0 is 0. The answer is 60. Now, we have two very different approaches that allow us to find the greatest common divisor. Approach number 1 is over here. The Euclidean algorithm. If factorization is unknown, probably our best approach is the Euclidean algorithm. However, if we know the factorization of both numbers, the best approach is this formula. Folks, any questions here?
I have a question. How do
Yes.
we know to what power to hold each digit to?
Well, please take a look at this. Here, index 1, here, index 1, here,
Oh, okay.
So we have 2 to fourth power here. We have 2 to second power here. So we can see the minimum of these two numbers, 4 and 2. Over here, think about 7. 7 to first power. Here there is no 7, means 7 to 0 power. Minimum of 0 and 1 is 0. There is no 7 here.
So the In this particular example, the factorization is already given to you.
Yes, absolutely. As I said, if factorization is given, the best approach is to use this formula in order to find the greatest common divisor.
Perfect. I was just not sure if it was given or not.
Yes. So did I answer your question?
Yes.
Next, the least common multiple of two positive integers a and b is the smallest positive integer that is divisible by a and b. So do not confuse greatest common divisor and least common multiple. Let us compare. So the greatest common divisor is the largest common divisor. Least common multiple is the smallest positive integer that is divisible by a and b. We denote the greatest common divisor by a comma b in parentheses. We denote the least common multiple by a comma b in square brackets. One can check that the least common multiple of 15 and 21 is 105, because 105 is the smallest positive integer, which is divisible by 15 and 21. The least common multiple of 24 and 36 is 72. The least common multiple of 2 and 20 is 20. The least common multiple of 7 and 11 is 77. Question is how to find the least common multiple. Please take a look at this formula. And by the way, compare this formula with this. In order to find the greatest common divisor, we raise each p to the following power minimum of alpha I, beta I. In order to find the least common multiple, we raise each p to the power maximum of alpha I, beta I. So this is pretty confusing. Here, least, but here maximum, here greatest, but here minimum. The reason why we put here minimum is the following. Greatest common divisor means the largest number that divides both A and B. Note that the largest power of P1 that divides both this and this is P1 to the smallest power, minimum of alpha 1 and beta 1. Because if power of P1 bigger than minimum, then this factor will not divide either this or both. Similarly here, to make sure that this is divisible by both, we should raise, for example, P1 to the biggest power, to maximum of alpha 1 and beta 1, and so on. Lastly, let us prove the following formula. The least common multiple is equal to AB divided by the greatest common divisor of A and B. So this formula gives us a relationship between a least common multiple and greatest common divisor. Indeed, by this formula, the product of the least common multiple and the greatest common divisor is equal to AB. Well, here is why. Let us factor A. Done. let us factor B. Done. For convenience, let us denote maximum of alpha j, beta j by capital MJ, minimum by a lowercase mj. Here is what we do. According to these two formulas, formula number 2 and formula number 1, what is written here, the least common multiple is equal to this, and the greatest common divisor is equal to this. Of course, we keep in mind these notations. Now, P1 to capital M1 times P1 to lowercase m1 is equal to P1 capital M1 plus lowercase m1. We do same here and so on here. One can show, and I will show you in a moment, we show it over here, that maximum of x and y plus minimum of x and y is equal to x plus y. It's exactly how we jump from here to here. Maximum of alpha and beta, which is this, plus minimum of alpha and beta, which is this, is equal to alpha plus beta. After that, split this into two pieces. P1 to alpha 1 plus beta 1 is equal to P1 to alpha 1 times P1 to beta 1. Similarly, split this into two pieces and so on, split this into two pieces and reshuffle the terms. We will get this. Lastly, what is written here is A, or what is written here is B. Proof is completely done. Finally, let us prove this lemma maximum plus minimum is equal to x plus y. Let us consider two cases. Case 1. Suppose x is greater or equal to y. In this case, minimum is y, maximum is x, and therefore, indeed, minimum plus maximum, which is over here, is x plus y. Done. Similarly, if x is lesser than y, case 2, minimum is x, maximum is y, and therefore maximum plus minimum is x plus y again. Think about questions.
Do B and A have the same number of prime factorization?
Very good question. Your question is why here we have n and here we have same n. Is this your question?
Absolutely, yes.
Yeah. So it's an excellent question. Let me go back to this example. Note that over here we have 3 prime numbers, 2, 3, 5. Over here we have 4 prime numbers, 2, 3, 5, 7. So it looks like over here n is equal to 3 and here n is equal to 4. Guys, know that what is written here can be rewritten as the following. This times 7 to 0 power. Therefore, we can assume that over here we have n prime numbers and over here we have n prime numbers, meaning the following. Sum of these alphas or sum of these betas are equal to 0. Does this answer your question?
Absolutely. Thank you.
Other questions?
For the max function,
Yes.
how we do it is the max of alpha j and beta j. It's just talking about the bigger number between the two, right?
Yes.
Oh, okay.
For
And the
example,
minimum
if
is the opposite.
For example, if alpha j is 2, beta j is 3, capital MJ is 3.
Oh, okay.
Or
Got it.
case
Thanks.
MJ is 2.
Oh, okay. All right. Thanks.